Okay, welcome back. Uh, so today I'm going to talk about the MOSFET, especially the effective mobility in the MOSFET and bulk charge theory versus the square law that we have studied. And body effect parameter, what is that? And the channel length modulation, how to parameterize the channel length modulation event. We're gonna adopt a new parameter denoted as a lambda. And uh, after wrapping up all the stuff for the N-channel MOSFET, then we are going to study how to understand the current voltage characteristic of P MOSFET. Afterwards, we're gonna wrap up this lecture note with some study on small signal model for the MOSFET. Okay, let's move on to the first topic, which is effective mobility. Well, the effective mobility mu sub EF of carriers in the MOSFET channel is a critical parameter that directly affects current flow. For small values of VDS in the linear region, definitely the MOSFET behaves like a resistor with resistance value of here. Yeah, RDS is equal to VDS over IDS. And that can be rewritten with some parameter of channel length, channel width, effective mobility herein, and effective oxide capacitance, and overdrive voltage VG minus VT stuff. So this resistance RDS depends inversely uh, on the effective mobility, mu sub EFF. Okay, so higher mobility means lower resistance, and which indicates a more current can be flown. So just as a slippery water slide lets water flow faster than a rough one. Okay. So the effective mobility differs from bulk mobility that we have studied in device physics because carriers in the emergent layer experience additional scattering mechanisms. Think of it like driving on a highway versus a crowded city street. Your average speed, which is corresponding to the mobility, is much lower in the city because of more obstacles and interactions. So in MOSFETs, three main scattering mechanisms affect mobility. Number one is a Coulombic scattering event. Scattering, which is coming from charged impurities. Okay, and another scattering mechanism is phonon scattering. Which is caused by thermal vibration in the silicon diamond crystal. And number three is the surface roughness. Surface roughness. Okay. Which comes from the silicon oxide interface, definitely. So as the gate field increases, carriers are pushed closer to the interface, making surface roughness scattering more significant and reducing mobility. So this is why effective mobility decreases at higher gate voltages, like how driving becomes slower as you get closer to a construction zone with a rough road surface. Okay. So understanding and modeling effective mobility is very crucial for accurate device simulation and circuit design. So modern devices use various techniques to enhance mobility, such as strained silicon, or different crystal orientations, similar to how highway engineers use better materials and designs to allow faster, more efficient travel. Okay. All right. So now let's move on to the next slide. Effective mobility versus effective normal field. So this graph illustrates how effective mobility varies with effective normal electric field in both NMOS and PMOS. The vertical axis here shows carrier mobility, while the horizontal axis represents the effective normal field. Okay, so here effective normal field. So calculated differently for NFET and PFET. Okay, so this is for NFET, this is for PFET. All right. Several important trends are evident. First, electromobility, upper curve, this guy, is significantly higher than whole mobility, lower curve, okay? Maybe about 2 or 3 times greater under comparable conditions. This is why NMOS transistors generally provide more current than similarly sized PMOS transistors, like how sports cars move faster than trucks, even on the same road. Okay, so now let's move on to the second one, mobility. Mobility decreases as the effective field increases for both carriers, right? Electron and hole. Mobility decreases as the effective field increases. So this occurs because higher fields push carriers closer to the silicon oxide interface, where scattering is more pronounced. So imagine walking on a beach. You move more quickly on the firm, wet sand, than in the soft, dry sand near the dunes. Okay. So let's take a look at the third point, number 3. Different substrate doping here. Different substrate doping concentrations shown by different markers affect mobility definitely, even particularly at lower field. Okay, so this is because the doping concentration affects coulombic scattering effects. Okay, so if I'm asking you why the substrate doping concentration affect mobility, which is more pronounced at lower electric field, then the answer is the doping concentration affects coulombic scattering effects. Okay, so understanding these mobility trends, this and that, is very critical for device modeling and circuit design. So by accounting for mobility variation with electric field, designers can more accurately predict device performance under various bias conditions. So this knowledge has guided us the evolution of CMOS technology, leading to innovations like a strain engineering, then enhanced mobility, that enhanced mobility. Similar to how understanding road friction has led to better tire designs for vehicles. Okay. All right, now let's move on to the next slide. Problem with the square law theory. You may think that, well, the square law theory would be very kind of idea and very simple, easy to use, easy to adopt, and easy to use for hands-on circuit analysis. That's right. That's the reason why we are saying that it has its own problem with the square law theory. So we need to figure out what kind of problems are included in the square law theory. So the simple square law theory that we have discussed before has a fundamental limit. That model ignores the variation in depletion width with distance along the channel direction. I'm talking about here. take a look at the depletion layer thickness along the X direction or along the channel direction. Okay, definitely, well, in general, we are applying a higher voltage on the drain node than source node because the substrate is P-type. So if you think of this PN junction and another PN junction on the source side, you may think that, well, the PN junction on the drain side would be more negatively biased for a given voltage once the substrate is grounded. Okay, so the square law theory has ignored the variation in depletion width along the channel. So in our first order approximation, we simplified the expression for the inversion charge to Q inversion is approximately equal to minus CXE times Vg minus Vt plus Vs minus Vc. So while this simplification makes the mathematics more tractable, it doesn't fully capture the physics of real devices. Looking at the diagram, you can see that the depletion region beneath the channel actually widens out from source to drain when a positive bias or positive VDS is applied. So this is very similar to how a river might be shallow at its source, but becomes deeper as it progresses downstream. Okay. So this variation I'm talking about here, so this variation affects the threshold voltage along the channel and the relationship between terminal voltages and current. In modern aggressively scaled down short channel devices, this effect becomes increasingly significant, making the square law model less accurate. It is like how a simple map works fine, okay, for short distances, but fails definitely to account for the Earth's curvature over long distances. So in the next slide, we're going to introduce a modified model that can address this limit by accounting for the bulk charge effect, giving us more accurate predictions of device behavior. Just as modern navigation systems improve on simple maps, these enhanced models allow for more precise circuit design and analysis. Okay, so now let's move on to the next slide, modified model or bulk charge model. So to account for the varying depletion width along the channel direction, we should introduce a modified model, which is known as bulk charge model. So this model incorporates a parameter M. Okay? M is denoted as the bulk charge factor, which is typically greater than 1. If M is 1, the bulk charge model is equivalent to the square law model. So M is denoted as 1 plus CD divided by CRC, and which is redescribed with the TRC and the depletion width as threshold condition. So this M factor reflects the effect of the depletion layer capacitance relative to the oxide capacitance. Okay, here and there. Right? So this M factor reflects the effect of depletion layer capacitance relative to oxide capacitance. Think of it as similar to having two springs in series. The effective spring constant differs from either individual spring. Okay. So with this modification, with the M factor greater than 1, the equations for the drain current become in linear region, VD is smaller than VD set, and you can redefine, you can rewrite the IDS current in the linear region as described in this equation. Take a look at this equation. Only m factor has been included. Otherwise, the equation itself quite similar to the equation that we have seen in square law model. Well, plug in the value of 1 into the m factor, then you may see that wow, this equation is quite equal to the equation in square law model. But in this modified model or bulk charge model, m is usually greater than 1. Okay, what about in the saturation region? If VD is higher than VD set, then saturation drain to source current is written with this equation. Take a look at the equation again. If you plug in one value into the M factor, then the old equation would be quite identical to the equation that we have seen in square law model. So here, notice that the key differences from our earlier model, square law model, the saturation voltage is now VD set. Saturation VD set is equal to Vg minus Vt over M. Okay, this is a one key difference. And the saturation current includes M, okay, in the denominator. Okay, so this accounts for the reduced inversion charge because of what? Yes, because of the bulk effect. So the graph on the left-hand side shows how this bulk charge model accurately predicts the current voltage characteristics for different gate voltages, right? The data, measured data is well fitted into the estimated lines. Each curve rises linearly at first, then gradually flattens as VDS increases, okay? Ultimately reaching saturation. The higher the gate voltage, the higher the saturation current, as we had expected from our bulk charge equation. So this modified model provides more realistic prediction of device behavior, especially as physical dimension of device shrink down, which is similar to how advanced weather models improve upon simple forecasting methods by accounting for more physical factors. Okay. Now let's move on to the next slide on MOSFET threshold voltage, V sub T. So the threshold voltage VT expression we derived earlier represents the gate voltage, reference to the body definitely, required to reach the threshold condition. So the threshold voltage is equal to flat band voltage, source to body voltage, 2 times the surface potential, 2 times bulk potential, and more. So in most circuit applications, however, we reference all terminal voltages to the source rather than the body. Okay, so this simplifies our analysis actually and better reflects how devices are used in circuits. So when VSB is 0, in other words, the source connected to the body actually, the expression above simplifies to Vt is equal to V flat band voltage 2 times bulk potential plus others. Okay. Then, let me see, using this source reference the voltages, our drain current equation becomes in linear region, ID lean is equal to the equation shown here. And in saturation region, the saturation drain to source current can be written with this, okay? And denote that VD set is equal to overdrive voltage to over M factor. So this formulation aligns better with how we think about circuits. where the source often serves as the local reference point. It is similar to how we might measure household water pressure relative to the entry point rather than street level. Okay. I mean, the entry point is corresponding to the source in MOSFET, and street level indicates the body region in MOSFET. Okay, so again, this is very similar to how we might measure household water pressure relative to the entry point rather than the street level. So these two equations provide the foundation for both hand analysis and computer simulation of MOSFET circuits, allowing circuit designers to predict the performance before fabrication. So saving time and saving resources and cost, much like how architectural models help builders visualize structures before construction begins. Okay. Now let's move on to the body effect. The stressor voltage VT is not constant actually, but varies with the source to body voltage VSB. So this phenomenon, known as the body effect, is represented by stressor voltage is equal to VT naught without any body effect plus body effect parameter gamma times some other factors. So here in the gamma is given by square root 2 times unit charge, doping concentration in body, and dielectric constant of silicon over oxide capacitance. So when the source body PN junction is reverse biased, I mean the VSB is greater than 0, then the threshold voltage increases. So this is like how increasing spring tension makes a door harder to push open. Physically, the reverse bias widens out the depletion region under the channel, requiring a higher gate voltage to create inversion layer. So for circuit designers, the body effect presents both challenges and opportunities. In many different types of integrated circuits, all NMOS transistors share a common substrate, meaning that the transistors at different positions in a circuit may experience different body effects. The circuit designers typically aim to minimize gamma value to ensure consistent performance across all transistors, like ensuring all doors in a building require the same force to open, regardless of their location. However, the body effect can also be intentionally utilized in some circuit designs, such as substrate bias generators or variable threshold logic. So understanding and controlling this body effect is crucial for advanced analog and digital design, definitely. So which is very similar to how understanding how temperature affects materials allows engineers to compensate for or exploit these effects in their designs. Okay. So now let's move on to the MOSFET threshold voltage measurement. Well, the question is how to measure the threshold voltage in your MOSFET. Well, measuring the threshold voltage of a MOSFET is fundamental for device characterization and process control. One common method involves plotting IDS versus VGS at low constant VDS value, usually 50 millivolts in modern devices. So in this approach, we operate the transistor in the linear region by extrapolating the here at low VDS. So by extrapolating the linear portion of this curve, To the x-axis, where IDS is 0, we can determine the threshold voltage. This is similar to finding the freezing point of a substrate by measuring its properties at various temperatures and extrapolating to where phase change occurs. As you might have studied in material science class. So the graph illustrates this procedure that I have just mentioned, showing the drain current rising approximately linearly once VGS exceeds VT. So the x-intercept of this linear region provides our threshold voltage measurement. So below VT, well, only a very small threshold, sub-threshold current flows, creating the nearly flat region near the origin. I'm talking about here. But in modern CMOSFET devices, IDS versus VGS, if I draw it with log scale on the y-axis, you may get this curve. So for a given IDS current level, usually 10 nanoamp or 100 nanoamp, it depends on company. Using this constant current level of IDS, you can extract out the threshold voltage. So just to find out the crossover point, and you can read out the gate to source voltage for a given constant IDS value. Okay. So this threshold voltage measurement technique has been widely used in semiconductor manufacturing in order to monitor process variations and ensure consistent device performance. So just as bakers measure ingredients precisely to ensure consistent results, chip manufacturers measure threshold voltages carefully to maintain product quality. The various refinements of this basic approach exist to account for mobility degradation and other second-order effects, providing us with even more accurate threshold voltage extraction. Okay. All right. Now let's move on to channel length modulation parameter, lambda. As we have discussed earlier, when VDS, drain to source voltage, exceeds VD set, the channel pinches off, right? Pinch off point is pointed out here, near the drain side. So creating a depletion region of with delta L between the pinch off point here and the drain. Okay. This effectively reduces the channel length from L to L minus, yeah, L minus delta L. So since the drain current is inversely proportional to channel length, this reduction causes the current to increase slightly with increasing VDS beyond saturation. So mathematically, ID set is proportional to the 1 over L minus delta L. And with the help of mathematics, this is equivalent to the 1 over L times 1 plus delta L over L. So the width of depletion region is actually proportional to the VDS minus VD set, right? So we can express this relationship using the channel length modulation parameter lambda. We can read, right, delta L over L. So incorporating this effect, the saturation current equation becomes, ID set becomes the equation that's shown in here. So this equation explains why real MOSFETs don't show perfectly flat saturation region because of this trap. Okay? So instead, the current continues to increase slightly with VDS increasing, with increasing VDS. So creating a non-zero slope in output characteristic. I mean, the IDS versus VDS plot, the non-zero slope can be found. But this is similar to how A stretched rubber band doesn't maintain exactly the same tension if stretched further beyond its elastic limit. Okay, so the channel length modulation effect becomes more pronounced in short channel devices where delta L represents a larger fraction of the total length L. So in modern nanoscale transistors, this and other short channel effects significantly impact device behavior, so requiring more sophisticated models than the simple square law theory. Understanding these effects is critical for accurate circuit simulation as well as to design in advanced technology nodes. Okay. All right. Now let's move on to the p-channel MOSFET now. Let's now turn our attention to the p-channel MOSFET from now on. Which p-channel MOSFET serves as the complementary counterpart to the NMOS in CMOS technology. The P MOSFET operates with charge carriers, which is holes, and voltages of opposite polarities compared against the NMOS. The AP MOSFET turns on when VGS is smaller than threshold voltage of P MOSFET, where VTP is a negative value, okay? So when it is activated, holes flow from uh, the source to drain, which means that the drain is biased at, P MOSFET here, P MOSFET turns on when VGS is smaller than VTP, which is negative. And when this P MOSFET is activated, holes flow from source to drain, okay? Which means the drain is biased at lower voltage compared against the source. Okay, so this is usually connected to the power supply voltage, and this VD is lower than power supply voltage. So the holes are moving from source to drain. Okay, in other words, IDS, ID minus IS is negative. Okay, well, in MOS, it was IDS is positive, but this is PMOS, right? So once PMOS is activated, the holes are flowing from source to drain so that IDS is negative. So think of it as water flowing downhill, but with the hill inverted compared to the NMOS. Okay. So in CMOS technology, the threshold voltages are typically designed to be symmetric. I mean, the VTP is equal to minus VTN. This symmetry simplifies circuit design by making NMOS and PMOS devices behave as complementary counterparts. So for PMOSFET, VDS is again negative, IDS is negative. In other words, VSD is positive, ISD is positive. And the magnitude of IDS increases with the magnitude of VG minus VT, as well as with increasing VDS, the magnitude of VDS. In other words, ISD increases with VSG minus VTP, the magnitude of VTP, as well as with increasing VSD. Okay, so be careful to what kind of polarity should be used when you are describing the electrical behavior of the P MOSFET. So see. So the diagram shows here. The diagram shows the structure of a P MOSFET built in a N-type kind of substrate or end well, okay, onto the P-type substrate. If I'm using a single well CMOS process, so with a P plus source, P plus regions for source and drain. Okay. So the operation of P MOSFET is analogous to the NMOS but with reversed polarities. Okay, so like driving on the opposite side of the road, but following the same traffic rules. So this complementary behavior is what enables the efficient low power operation of CMOS digital circuits that dominate modern electronics. All right, now let's move on to the next slide, PMOSFET current versus voltage. With so many equations. So the current versus voltage characteristics of a p-channel MOSFET mirror those of the n MOSFET, but with reversed polarities. The drain current equations are as follows. In linear region, the IDS can be described with this equation, but in saturation region, the IDS can be described with the equation as shown in here. So it is noteworthy that for PMOS, uh, both VDS and VG minus VT are negative, and, and consequently, IDS is also negative. However, in practice, we often work with the magnitudes of these values. Okay, so the bulk charge vectors M here, 1 plus 3 times the TRC over WT applies to PMOS just as it does to NMOS, accounting for the depletion region effects beneath the channel. So one significant difference of PMOSFET from NMOSFET is that pole mobility, mu P effective, is typically 2 or 3 times lower than the electron effective mobility. So this means that PMOS transistors must be wider than the NMOS transistor to achieve what? Yes, to achieve the same current drive capability in digital circuits, which is like needing a wider lane for slower moving traffic to maintain the same flow rate on the road. This mobility difference is why many CMOS designs use wider PMOS devices to balance performance between the two transistor types. Despite of these differences, the fundamental physics and equations governing PMOS operation parallel those of NMOS, making the complementary approach of CMOS both elegant and powerful for circuit design. So this symmetry in behavior, despite asymmetry in physical parameters, is what makes CMOS technology so versatile and efficient. Okay. So now let's move on to the small signal model, which should be the last. No. A few more slides left. For analyzing MOSFETs in amplifier circuits, we often use a small signal model that linearizes the device behavior around an operating point. Well, this small signal model, represents how the transistor responds to small changes in voltages and currents, rather than their absolute values. So the key parameters in this small signal model are the transconductance, GM, and output conductance, G sub D. The GM can be defined with this equation as shown in here, and G sub D can be written with this equation. So the transconductance G sub M quantifies how effectively the gate voltage controls the drain current. Okay, and as described in this differential term. Higher GM means better voltage gain capability, which is like how a sensitive steering wheel provides better control over a vehicle's direction. The output conductance G sub D, GD, represents the slope of the ID versus VD curve in saturation, okay? Which ideally would be zero, but it is non-zero because of channel length modulation, okay? So that's the reason why you may see the lambda parameter for channel length modulation. So these parameters define the small signal behavior through the equation of this. ID is equal to GM times VG plus GD times VD, where lowercase letters here, I mean here, there, here, there, where lowercase letters represent small signal variables. So this small signal model represented by the equivalent circuit shown in this slide with with figure B. The current source controlled by the gate voltage and the output resistance representing channel length modulation effect. So this simplification allows engineers to analyze complex circuits using linear techniques, which is much like how small angle approximations simplify trigonometric calculations. Okay? So for higher frequency analysis, capacitive elements are added to model the dynamic behavior. So take a look at these two capacitive model components. We are going to discuss these in a future lecture. Okay, so this small signal approach forms the foundation of analog circuit design, enabling the creation of amplifiers, filters, and other signal processing blocks. Okay. Now let's move on to the next slide. Inclusion of additional prosthetics. While our basic small signal model well captures the core transistor behavior, real MOSFETs include additional prosthetic elements that become increasingly important at higher frequencies and in smaller devices. The diagram shows a more comprehensive model that includes gate to source capacitance and gate to drain capacitance. And another one is overlap here. The gate electrode is overlapped with the source side. So the overlap capacitance between gate and source, and another overlap capacitance between gate and drain. And here's source and drain series resistance value, and body to source here, body to source, and body to drain, resistance to resistance, and to capacitance between body and source, and or between body to drain. So these prosthetic elements arise from the physical structure of these MOS devices. For example, the gate overlaps slightly with the source and drain regions, creating overlap capacitance, which is definitely prosthetic. The source and drain regions have finite resistance, Rs, S, and Rd. Even though the source drain regions are heavily doped, still, source drain itself has its own resistance. And there are another PN junctions between these regions, right? From source drain to body. So at much lower frequencies, many of these parasitics can be ignored. Okay, at lower frequency, if MOSFET is working with low frequency, many of these parasitics that I have just mentioned can be completely ignored. However, they become dominant limits at high frequency. The gate capacitance, for example, slow down switching speeds as they must be charged and discharged during transitions, which is like how a heavy steering wheel makes a car less responsive to quick directional changes. So understanding and modeling these prosthetics is critical for high frequency circuit design rather than low frequency circuit design, as well as which is this understanding modeling these prosthetic is also critical for RF radio frequency applications and high speed digital systems. So advanced process technologies continuously strive to minimize these prosthetics, just as sports car designers work to reduce undesirable characteristics that limit performance of the sports car. So as devices scaled to nanometer dimensions, accurate modeling of these parasitic effects becomes essential for successful circuit implementation in the end. Now let's move on to the next slide, cutoff frequency. Well, the cutoff frequency, or Fmax, represents a fundamental limit on a MOSFET's ability to amplify signals. It is defined as the frequency at which the transistor's current gain drops to unity or 0 dB. Well, mathematically, this Fmax is given by the Gm over 2 pi times the CoxE. Well, this expression reveals several important insights. Number one, Fmax is inversely proportional to the square of the channel length here. And this explains why reducing channel length dramatically improves the frequency response. Making the channel length half enabled to quadruple Fmax, which is similar to how reducing a car's weight significantly improves its acceleration. And number two, Fmax increases with gate overdrive voltage, or Vg minus Vt. Operating at higher overdrive improves frequency response, though at the cost of increased power consumption, definitely. A common trade-off in electronics, which is like how a car can go faster by burning more fuel. Number three, higher carrier mobility directly increases Fmax, which is why 3-5 compound semiconductors with higher mobility are often used for high-frequency applications instead of silicon. So the continual drive toward the smaller transistors in each new technology node is largely motivated by this relationship between channel length and cutoff frequency. So modern nanoscale MOSFETs can operate at frequencies well into the gigahertz range, a few hundred gigahertz, approaching to the terahertz now, enabling high-speed computing and wireless communications. So understanding these frequency limits helps circuit designers optimize their own circuit designs for required bandwidth while managing power consumption. So balancing performance against efficiency. Just as vehicle designers balance speed against the fuel economy. Okay. So now that all the contents concludes our lecture on MOSFET theory and operation. So in next class, we will explore. We may have look for some time to explore advanced topics, including modern device structures and emerging technologies that address the limit of conventional MOSFET. Okay, student presentation will be followed definitely, as I have posted on the announcement. Okay, so that's all for today's lecture, and I hope you to enjoy the how the MOSFET is working in real world. I would like to recommend you to read out some the chapters corresponding to the MOSFET operation. All right, that's all. Thank you very much, and thank you for your attention.